Hello students, in this video lecture I'm going to discuss the concept of bottom element and top element in partially ordered sets. So first of all, let us understand what do you mean by a top element in a PO set. So let P less than equal to be a PO set. Then an element A belonging to P is said to be top element of the partially ordered set P if X is less than equal to A for all X belonging to P, which means that every element of the partially ordered set P is smaller than A, or every element is lesser than A, or in other words, A is greater than every element of the partially ordered set P. So if you try to draw the hash diagram for the partially ordered set P, because A is greater than every element of P, this means that when you draw the hash diagram, A will be at the top and every element of P will be lower than A. And in that sense, A is called the top element. Now it is not necessary that if we are given a partially ordered set, then it will always have a top element. It may have a top element, it may not have a top element. In case P has a top element A which behaves like this means that A is greater than every element X of P, or every element X of P is smaller than A. In that case, we say that P has a top element, and in that case the top element is denoted by capital T. So if capital T exists, which means that if top element exists in a partially ordered set P, then the top element which is capital T, which is denoted by capital T, will always satisfy this particular condition, and the condition is that every element X of P will be smaller than T, or every element X of T will be lesser than T, or T will be greater than every element of the partially ordered set P. So this is the definition of the top element. Let us take a few examples. So consider the PO set, power set of X with respect to inclusion relation. We have already seen that if X is any set, then the power set of X, that is the set of all subsets of X, is a PO set with respect to the inclusion relation, or with respect to the relation is subset of or is contained in. Capital X can be taken to be any set. In particular, in this example, we have taken capital X to be the set 1, 2, 3 consisting of 3 elements. So power set of X will consist of 2 to the power 3 elements, because capital X has 3 elements. So accordingly, power set of X, which is subset of, which is set of all subsets of X, has 2 to the power 3, which is 8 elements. And if we list out those 8 elements of power set of X, then those 8 elements are the empty set. Then subsets consisting of single elements or one element, that is singletons, singleton 1, singleton 2, singleton 3. And then subsets of X consisting of 2 elements each, which means the set 1, 2, the set 1, 3, the set 2, 3. And then last is the set X itself, which is the set 1, 2, 3. So these are the 8 subsets of X, and we have already seen that when you draw the hash diagram for the PO set, power set of X, where X is consisting of 3 elements 1, 2, 3, then this is how the hash diagram looks, where phi, which is the empty set, is at the bottom, and X, which is the whole set, is at the top. And we can just see that every element of this PO set, power set of X, is below or is smaller than capital X. So this means that capital X in a way is behaving like the top element, because this capital X is an element in the power set of X, which is such that if you take any element A belonging to power set of X, then every element A belonging to power set of X will be contained in X, or it will be smaller than X, because in this case the relation is contained. So less than equal to, the relation less than equal to is contained. So every element A is smaller than X. So this X, or the whole set X, is behaving like the top element. So this is the top element T in the PO set, power set of X. So this is an example of a PO set which has a top element, and the top element is given by the set X itself, which is the underlying set whose subsets are taken in the power set. Then coming to the second example, if we consider the PO set n less than equal to, where n is the set of naturals and less than equal to is the usual less than equal to relation, the usual sense in which we understand less than equal to sign, then we already know that this n less than equal to is a PO set. In fact, it's a chain. We have already done this earlier. And if we just try to draw the hash diagram of this particular PO set, or if we try to draw the diagrammatically, if we try to visualize this PO set, this particular chain, then this is how this chain looks. At the bottom you have the natural number 1, and then 1 is related to 2, and then 2 is related to 3, and so on. Because the set of natural numbers is infinite, so we don't have a well-defined hash diagram for it, but somehow this is how the hash diagram looks. So you can see from the hash diagram itself that there is no top element, there is no element which is at the top. Otherwise also, when you give the mathematical argument that this particular PO set has no top element, or it has no element at the top, we can say that there is no natural number n. You cannot find any natural number n which is such that every natural number x is less than that. So there is no natural number n such that every natural number x is less than that. The moment you say that n is the top element, you will get a natural number n plus 1 which is greater than n. So this means that n cannot be a top element. N cannot be greater than all the natural numbers, because there will always be a natural number greater than it. So the PO set of the set of natural numbers with respect to the usual less than equal to sign, which is a chain, does not have a top element, which can be verified from the hash diagram also. So this is an example of a PO set which does not have a top element. Now coming to a note. This particular note establishes the uniqueness of the top element. The note says that if for a given PO set P, top element T exists, then it will always be unique. So whenever the top element will exist, then the uniqueness of top element is assured. So we can prove the uniqueness of top element by using the anti-symmetry property of PO sets. And how do we do that? This is how the proof goes. If you take P less than equal to be a PO set, then let, if possible, suppose that P has two top elements, and let me denote those two top elements by T1 and T2, which means that T1 and T2 both are in P, and both of them are top elements, and eventually in the end we will show that T1 and T2 finally will come out to be same. So this is what we will show in the end. Now first of all, because T1 is top element, so by using the definition of top element, T1 must be greater than every element of P, which means that every element x of P should be smaller than or less than equal to T1. So this is by definition of the top element. This line, this particular line which I am calling as 1, this particular statement should hold, this particular statement 1 should hold for every x belonging to P. In particular, it should hold if you take x as T2 also, because T2 is also an element of the partially ordered set P. So replacing x by T2, you have that T2 is less than equal to T1. This is one relation that we get, which we are marking as star. So here you have used the fact that T1 is a top element. Now using the fact that T2 is a top element, because T2 is a top element, so this means that T2 should be greater than equal to every element x of P, or every element x of P should be less than equal to T2. So in particular, if you take x to be equal to T1 belonging to P, because T1 is also an element of P, replacing x by T1 in this relation, which I am calling as 2, we get that T1 is less than equal to T2. I am replacing x by T1. So this relation star dash we get, and this relation star dash is obtained by using the fact that T2 is the top element. So there are two relations that we have in hand. The two relations are star and star dash. One says that T2 is less than equal to T1. The other says that T1 is less than equal to T2. By anti-symmetry, because we are in a partially ordered set P less than equal to, where anti-symmetry holds, and by anti-symmetry property, whenever you pick up any two elements A and B belonging to P, such that A is less than equal to B and B is less than equal to A, then they together always imply that A is equal to B. So by anti-symmetry property, you have that T2, because T2 is less than equal to T1, and because T1 is less than equal to T2, so you have that T1 is equal to T2, which means that there is no distinction between T1 and T2, and they are exactly the same, and so you can denote them by T. So this means that the top element, whenever it exists, is unique. So this proof establishes the uniqueness of the top element. Now coming to a parallel concept, which is the concept of bottom element in a PO set. So let us now give the definition of bottom element in a PO set. So let P less than equal to be a PO set. Then an element B belonging to P is said to be bottom element of the PO set P if B is less than equal to X for all X belonging to P, which means that B is smaller than every element X belonging to P, or B is lesser than every element X belonging to P, or every element X belonging to P is greater than B. So if we try to draw the hash diagram for P, then because B is smaller than every element X belonging to P, so B will always be at the bottom and every element of P will be above B. In that sense, B is called the bottom element of the PO set P. So again, as in the case of top element, again it is not necessary that given a PO set P it will always have a bottom element. The PO set P, given PO set P may have a bottom element, it may not have a bottom element. In case the given set P, the PO set P has a bottom element, then the bottom element is denoted by inverted T. And so inverted T, if it is a bottom element, in that case it should satisfy this property, that inverted T, which is the bottommost element or bottom element, should be less than equal to X for all X belonging to P, or bottom element should be smaller than every element of P, or it should be lesser than every element of P, or every element X of P should be greater than the bottom element. So let us come to a few examples. As we did in the case of top element. Now consider the PO set power set of X with respect to inclusion relation. We have considered this PO set when we were discussing top element. Now this PO set power set of X with respect to inclusion relation, we know very much it's a PO set where capital X is any set. In particular, capital X has been taken as 1, 2, 3, as we did when we were discussing the top element. And we have already seen that the power set of X, which is the set of all subsets of X, has 2 to the power 3 elements, which is 8 elements, and these 8 elements have been listed. And the hash diagram for power set of X has been drawn over here. And from the diagram of power set of X, it can be seen that the empty set phi is at the bottom, because the empty set phi is contained in A for all A belonging to the power set of X. If you pick up any element of power set of X, then phi will be contained in A for all A belonging to power set of X, which means that phi is smaller than or phi is lesser than every element A belonging to power set of X. So in a way, phi is acting like a bottom element, or phi is the bottom element inverted T in the PO set power set of X with respect to inclusion relation. So this is an example of a PO set in which bottom element exists. Another example of a PO set, if we consider the set of naturals with respect to the usual less than equal to relation, the usual sense in which we understand less than equal to sign. So we know that n less than equal to is a PO set, and if we try to draw the hash diagram for this PO set, although the set of natural numbers is an infinite PO set, and it's not, we will not get a very well defined hash diagram, but this is how the hash diagram of n less than equal to looks, where 1 is at the bottom and 1 is less than equal to 2, 2 is less than equal to 3, 3 is less than equal to 4, and so on. And we can see that the element 1 or the natural number 1 is such that 1 is less than equal to n for all n belonging to n. So 1 is smaller than every other natural number, which means that 1 is behaving like a bottom element. So 1 is the bottom element inverted T. So this is another example of a PO set in which bottom element exists. Then again consider the PO set of negative integers, which is -1, which is the set -1, -2, -3, and so on. The integers are going on decreasing with respect to the usual less than equal to relation, the usual less than equal to sign, the usual sense in which we understand less than equal to relation. And we can see that this particular set has no bottom element because the elements of this set are going on decreasing. There is no negative integer which can act as a bottom element. There is no negative integer which can act as inverted T, because there is no negative integer which is smaller than every negative integer. So there does not exist any negative integer z such that z is smaller than every negative integer, which means that this PO set doesn't have a bottom element. Then again consider another PO set, which is the set of integers with respect to the usual less than equal to relation, the usual sense in which we understand less than equal to relation. And this is again an infinite PO set, but this fails to have a top element and it fails to have a bottom element. Again, this particular infinite PO set doesn't have a very well defined hash diagram. If we try to draw the hash diagram of z less than equal to, then this is how somehow the hash diagram of z less than equal to will exist. There is no there is no greatest integer and there is no least integer, which means that there is no integer which can act as a top element and there is no integer which can act as a bottom element. So this is an example of a PO set in which there is no top element and there is no bottom element. Now coming to the fifth example. The fifth example is that for any anti-chain, if you pick up any anti-chain with more than one element, then it will neither have a bottom, it will neither have a top. So let us take an anti-chain of, let's say, 4 elements. So this is the hash diagram of anti-chain of 4 elements. Now out of these 4 elements which we have in the anti-chain, there is no element which is greater than all the 4 elements, which means that this anti-chain is failing to have a top element. Also, there is no element out of these 4 elements which is smaller than there is no element out of these 4 elements which is smaller than all the 4 elements, which means that this set doesn't have a bottom element also, because there is no element which is greater than all the 4 elements, there is no element which is smaller than all the 4 elements, which so this particular PO set doesn't have a top element, it doesn't have a bottom element. Now this was the explanation that we have given for anti-chain of more than one element, in particular anti-chain having 4 elements, but the same argument can be given if you take anti-chain of 5 elements or 6 elements or 2 elements or 3 elements and so on. So the anti-chain will fail to have, anti-chain of more than one element will always fail to have a top, and also it will fail to have a bottom. And coming to the last example is that a finite chain always has a bottom and a top. If we try to draw the hash diagram for a finite chain, then the hash diagram for a finite chain would look somewhat like this, whatever number of elements it has, but the diagram would look like this, which means that there will always be an element at the top and there will always be an element at the bottom. This element which is at the top is greater than all the elements, and this element which is at the bottom is smaller than all the elements. So this element is the top element and this element is the bottom element. So a finite chain always has a bottom and a top element, whereas an infinite chain need not have a bottom or a top element, as we have seen in the set of natural numbers with respect to the usual less than equal to sign here. This is an example of an infinite chain in which bottom element is existing but top element is not there. Again, this is an example of a chain, the set of integers in which is not having a top element, which is not having a bottom element. So in an infinite chain, anything can happen, but as far as a finite chain is concerned, it will always have a bottom element, it will always have a top element. Now coming to a note which establishes uniqueness of the bottom element. The note says that whenever there is a PO set which has a bottom element, whenever the PO set P has a bottom element inverted T, whenever it exists, then it is always going to be unique. So this is what the note says. It establishes the uniqueness of the bottom element. So the proof is again similar to the proof that we did for establishing uniqueness of top element, and the proof is like this. If you take P less than equal to be any PO set, And if possible, we suppose that P has two bottom elements. Let's say these bottom elements are inverted T1 and inverted T2. In the end, of course, we will show that inverted T1 and inverted T2 are both same. But if T1 is a bottom element, then by definition, this inverted T1 should be smaller than all the elements X of P. In particular, because T1 is smaller than all the elements X of P, in particular, if you take X as inverted T2, then also this particular statement is true. So in this statement, which I am calling as A, in this particular statement A, I replace X by this inverted T2. So this is the relation that you get, that T1, inverted T1 is less than equal to inverted T2, which I am marking as star double dash. Then again, here we have used the fact that inverted T1 is bottom element. Let me use the fact that inverted T2 is bottom element. Now because inverted T2 is bottom element, so inverted T2 is less than equal to X for all X belonging to P. Let me mark this as capital B. Now because this particular statement B is true for all X belonging to P, in particular if you take X as inverted T1, because inverted T1 is also an element of P, so if you replace this X by inverted T1, then also the statement B is true. So I replace this X by inverted T1, and this is the statement that you have, that inverted T2 is less than equal to inverted T1. And we are marking this statement as star triple dash. So there are two statements that you have. First is star double dash, the other is star triple dash. This is star double dash, that inverted T1 is less than equal to inverted T2, and star double triple dash says that inverted T2 is less than equal to inverted T1. And whenever such two statements hold together, then because we are in a PO set, P less than equal to is a PO set, and whenever there are two elements A and B belonging to P which are behaving like this, that A is less than equal to P and B is less than equal to A, then this together implies that A is equal to B because of anti-symmetry. So because of anti-symmetry, we will have that T1 will be equal to T2, which means that there is no distinction between inverted T1 and inverted T2, and both of them are actually same, and we can call them as inverted T. So this means that the bottom element, whenever it exists, it is going to be unique. And in fact, although we have proved the uniqueness of bottom element inverted T by giving a proof in the note which I have just given in this particular note, but the uniqueness of bottom element inverted T can also be established by using the uniqueness of the top element capital T, because we have already shown that the top element capital T is unique. This we have already shown. So this statement is already true, that capital T, which is the top element, if it exists in a PO set, then it is unique. We know that this statement is true. It has already been proved. And again, we already know that for partially ordered sets or PO sets, there is a duality principle. There is a principle of duality, that if a statement is true in PO sets, then its dual statement is also true in all the PO sets. So now, since this particular statement is true, so the dual statement, the dual of it will also be true, which means that as we were saying, that if capital T, if it exists in a PO set, is unique, so the dual statement of it, replace capital T by inverted T. Inverted T, if it exists in a PO set, is unique. This is also true, which is the dual statement by principle of duality. So this this particular note which uses principle of duality, this principle establishes the uniqueness of the bottom element by using the uniqueness of the top element. So that was all about bottom and top element.